click the red subscribe button right under the video and also the bell icon to get notification on any of our latest updates on our videos.
Hi guys, welcome to another tutorial of Smart PU Kites on the course Material Science. In our last class, we saw how to calculate the atomic packing factor of a BCC, which is body center cubic crystal structure. In this class, we will be talking about the FCC crystal structure. Here we are asked to calculate the atomic packing factor of FCC crystal structure, which is the face center cubic atomic packing factor. So let's dive in. So solution. So we know that the formula of atomic packing factor from our previous class is equal to volume of atom in unit cell, the volume of atom in a unit cell divided by the total unit cell volume, the total unit cell volume. And we also say that this is equal to the volume of atom in unit cell is equal to number of atom multiplied by the volume of atom, which is Na multiplied by Va, volume of atom, divided by the total unit cell volume, which is Vu. Let's call it Vu. And we said Va, since the atom are in spherical nature, so we can say the volume is 4/3 pi r cube. So, and our Na, we have to calculate our Na from the structure, and Vu is, we said Vu is equal to A cube. So firstly, for us to find our atomic packing factor, we have to find the number of atom. Therefore, we have to draw our crystal structure. Then we have to find the volume of atom, which is 4/3 pi r cube. So this r is the radius, and Vu is the total volume, total unit cell volume. So therefore, let me show you the schematic diagram of a face center cubic. So this is a schematic diagram of a face center cubic. As you can see here, we are having half of the atom at each face of the face center cubic. So that is why it is called a face center cubic. You can see we have half atom at each face of the cubic, which is, remember in our last class, we splitted our structure into pieces. Therefore, we make use of an example of a watermelon. Here also, I will be making use of a watermelon as a case study here. So, in order to simplify the FCC, we assume our atoms to be a watermelon. In our last class, I said if we divide this watermelon into two, we are going to have something like this. Therefore, this is 1/2 of our initial watermelon, and this is half of our initial watermelon, right? So if we further dividing this half that we are having here and this half that we are having here, we are going to have 4 pieces of our watermelon now. So therefore, we are having 1/4 here, 1/4, 1/4, if you didn't forget from our previous class. So further dividing this again into 2 pieces, each of the 4 into 2 pieces, we are going to have 8 pieces of our watermelon. Therefore, we are having 1/8, 1/8 here, 1/8, and so on and so forth for the rest. So applying this assumption here, assuming that this our atom are watermelon. So here you can see this is half. This is half of the watermelon. This is half of the watermelon in each face of the cubic, and at the edges of the cubic, we are having 1/8 of the what? We are having 1/8 of the atom, which is our watermelon that we divided into 8. So therefore, our number of atom now, our number of atom Na is equal to, we have 1/8. The watermelon we divided into 8 places around the edge of the cubic, which is 8 times. That is times 8. So now we are having plus, we are having half of the watermelon at each face of the cubic. And a cubic has how many faces? Our cubic has 6 faces. Let's use this diagram because this is what you are going to be using for the purpose of exams and thesis. So let's count our face here. We are having half of it: 1, 2, 3, 4, 5, and this one at the front, which is 6. So therefore, you can see we are having half of our watermelon. This one at the face at each face of the cubic, which is 1 over 2, and don't forget it is half of the watermelon, which is 1 over 2 times 6. So therefore our number of atoms is now equal to 8 will cancel 8, which is 1. 2 here is 1 and 2 here is 3. Therefore we are having 1 plus 3, which is equal to 4. Our number of atoms therefore is equal to 4. So therefore we are having 4 atoms in a FCC crystal structure. So now to find our number of R, since we've gotten the number of atoms, we are going to look for our R. So for a face center cubic, it is not as complex as a BCC. In our previous class, remember we manipulated the box in order to get our R. But here we are going to get our R straightforward, because an FCC crystal structure is not as complex as a BCC. So we said the distance between this place and this place is R. The distance between here and here is also an R. So therefore the entire distance from here to here will be 2R. So if you can see the entire line, this entire line is what? Is equal to 2R plus R plus R. This R plus this R plus this R. So therefore here, don't forget we are having A, and here also we are having A. So taking this is a right angle triangle. If you can see, let me use another pencil so that you can see this very carefully, so that you can see this properly. So looking at this very carefully, this is a right angle triangle. If you take it like this is a right angle triangle. Don't mind my drawing. So we're having a 90-degree here, 90-degree. So we can utilize Pythagoras theorem here, which said hypotenuse squared, our hypotenuse is 4R. After plus into R plus R plus R is 4R. Here we are having A, and here we are having A. So we are having hypotenuse squared, which is 4R squared, is equal to opposite squared, which is A squared, plus adjacent squared. So therefore we are having 4R squared is equal to 2A squared. So now making R subject of formula, we are going to be left with R is equal to 2A squared root 2 over 4. So therefore our R is equal to A root of 2 over 4. So we know that our number of atoms, we've calculated for our number of atoms. We said our number of atoms is equal to 4, and our R is equal to A root 2 over 4. So now we have all the parameters we are looking for. We can dive into calculating the atomic packing factor. So our APF is equal to number of atoms multiplied by volume of atom divided by volume of unit cell, and we know that our VU is equal to A cube. So therefore we are having, substituting all our parameters, now we are having Na is 4 times VA. We said VA is the volume of the sphere, which is 4 over 3 pi R cube all over A cube. So this is equal to 4 times 4 is 16 pi over 3 R cube. We said our R is A root 2 over 4 cube all over A cube. So this can be further simplified our APF. Sorry, here is APF. Our APF, atomic packing factor, is equal to 16 pi over 3 multiplied by A cube. If you cube this bracket, you are going to have A cube. Cube of root 3 is 2 root 3 multiplied by 2 root 3 over cube of 64. Cube of 4 is 64 over A cube. So A cube can cancel A cube. So here we are left with 16 pi over 3 multiplied by 2 root 2. Sorry, here is not root 2, here is root 3. So you have to be very carefully whenever you are calculating, because in mathematics, when you make a mistake, that is all. Your calculation will be totally wrong. So therefore we are having 16 pi over 3 multiplied by 2 root 2 over 64. So this can be further simplified into 16 times 2, we are having 32 pi root 3 all over 3 times 64. Divide by 192. So if you press this very carefully in your calculator, you end up with 0.740. So multiply this by 100% because atomic packing factor is calculated in percentage. So 0.74 multiplied by 100. So our answer is 74%. Therefore, our atomic packing factor for FCC is 74. So I hope you enjoyed this tutorial. I hope you understand what I just explained to you. If you are confused or you have any question, you can put it in the comment section. We'll meet in our next class. Thank you.